we're very happy to be here, and it's a pleasure to talk to you today. I hope it will be interesting also for you. We will bring you some of the concepts that we have been working on for the past 5-6 years, more or less now, and hope that they're useful also for your work and your studies, and hope also to have some exchange with some of you then maybe in the future. Generally, we'll give you a quick intro about ourselves. What is Eurac? What were the problems that we were facing in the beginning of these research and development activities that led us to actually starting those? And then we go in the first half of this morning for you. For now, for us, it's actually already after lunch, but we will go through OpenEO, give you all the backgrounds about OpenEO, which clients are there, some new concepts that we're developing currently about federating different cloud services, and some examples of our own backend here at Eurac. And then in the second part, after the coffee break or whatever that is, we will talk about SAR2CUBE and go into more details how to apply SAR processing with OpenEO in one of our recent research projects. Exactly. So we are from Eurac. Eurac is actually a private non-profit research institute. It has been founded about 30 years ago, or exactly 30 years ago. Actually, this year we celebrated our 30-year anniversary. It's a very diverse research institute with a large number of different topics, covering everything from environmental topics to linguistics to biomedicine, renewable energies, even studies about mummies and medicine, all kinds of different topics. And Eurac is also quite large now, about 600 people working here. And we are actually from the Institute for Earth Observation, Michele and myself. And our institute has 3 main objectives. That is Earth observation for environmental monitoring. That's the classic remote sensing, all the applications that you know how to do SAR, hyperspectral, multispectral data analysis, and apply it to important topics like cryosphere, vegetation, and so on. Then we have the group on climate and disaster risk that is applying all of the information that we can derive from remote sensing and other sources into climate modeling, climate analysis, impact assessment, risk determination, and all of the topics around that. And finally, you have the group Advanced Computing for Earth Observation, dealing with all the topics that you need from the data science perspective to deal with large data like we have in Earth observation, the data management part of all of our collections of satellite data that we host. We have, for example, all the data over the European Alps in-house, so it's quite a large archive, need to be managed and so on. And yeah, I'm the head of this group, and Michele is part of my team here today. And today we will also split it like this, that I will do the lecture parts of this session, whereas Michele will do the practical examples for you. Generally, our mission is to monitor and understand key environmental dynamics and the impact of climate change in mountain regions. So as we as an institute are located in the center of the mountain regions, a lot of the applications that we work on are also thematically in mountain regions. So we look, when we speak about cryosphere, we are not thinking about polar ice sheets, but we speaking about glaciers in the mountains, for example. And when we speak about agriculture, we speak about grasslands and vineyards and maybe apple trees, and not so much about wheat and corn and things like this, because this is the reality in which we live. Another key part of our mission is to share all of what we do openly and accessible, share the knowledge, the scientific findings, the data, and so on, which is also part of our involvement with OpenEO, which is really an open science project. In order to reach our goals, we really apply a range of scientific methods such as Earth observation, climate science, data science, modeling, risk assessment, and other interdisciplinary and participatory approaches. So really also reflected in the people working in our institute. So in the Institute for Earth Observation, about 40 to 50 people usually, and really with very diverse backgrounds from all kinds of fields come together there. just a quick introduction about us. So then let's go to OpenEO, or maybe before that to where did we start actually. A lot of the issues that we are facing today, we started around 2016-17 when we started in this ESA project, which was called SAR2CUBE. And there we simply had the objective to, after Sentinel-1 data was finally available, to exploit the not so commonly used SAR data for classical applications like land cover mapping and vegetation mapping. And then we also needed to do this collaboratively with a large set of partners. So we needed to share data with them, exchange algorithms, and develop new methodology with them. And do all of this on SAR data, and there we really started to work with the raw SAR data, so the SLC data, single look complex data, and we were kind of overwhelmed with the amount of data that we created during this project. We had more than 110 terabytes of data created there for various regions, and this was not something that was long-term sustainable for us, so we needed to find other solutions to better keep the SAR data and all the different products that you can derive from it, but not make our storage systems explode because of it, basically. There are a few interesting papers that came out of this project. You can have a look at them if you Google for them, which is one Sentinel-1 in SAR coherence for land cover mapping, which really exploits a little bit the different methodologies of classifiers that you can use and what their benefits are, and also what the benefit of using in-SAR coherence in general could be, where it works, where it don't work, and so on. And then a second paper, a little bit more specific on time series of Sentinel-1 interferometric coherence and backscatter for crop type mapping. So specifically for crop type mapping approaches and exploitation of time series. That's just where we basically started. So we had a lot of interesting data. We needed to share it, and it was quite difficult to achieve this with the technologies available at the moment. The next thing is then the data organization. So why data cubes? What is actually a data cube? So a data cube is a multidimensional array, so a digital struct with several dimensions. It's not necessarily a three-dimensional thing, as the word cube might say. You can have more than 3 dimensions actually. Most common, if you speak about 3 dimensions in a data cube, it's actually not X, Y, and Z in terms of spatial coordinates, but it's usually something like latitude, longitude, and time, or northeast and time, or just X, Y, and time, or something like this. But sometimes you then have also a Z component, and then it's already a 4-dimensional data cube. And later you will also see example with more crazy data cubes with several time axes, like in the case of coherence in the second part. Generally, these data sets, they're much larger than what you can handle in the memory of your workstation or laptop computer. So the idea is that you create large collections of data sets that have the same conditions, so that all the values are the same, that when you have a grid over the values, that they all reflect the same space on Earth and have the same extent and so on. And each axis is also following the same unit and so on. Key principles here are really that you only once have to do the pre-processing and then can reuse it many times. We will also see that with SAR2CUBE later. That was one of the things where we really were able to save a lot on the data requirements, because we found a way of describing our SAR data cube so that we can reuse it for many different applications without always needing to store everything persistently. The other thing is, most users don't actually need to work on the whole world or whole country or whole continent, but they need to work on a specific study area, which leads you to, you only extract from this data cube the data that you actually currently want to work at, which means that you can subset your data in space, in time, and maybe also in the features like the different multispectral bands, red, green, blue, infrared, or in the case of SAR, the polarizations, for example. And the next thing is then, since these data sets are very large, it's also important that you bring the processing to the data. What you don't want to do is move the data all the time around, because that's quite time consuming if you start to copy around terabytes or even petabytes of data every time you switch to a different cloud computing center or so. So you try to implement the processors, the thing that you want to do with the data, in the cluster next to where the data is stored, so that this is efficient and not so time consuming, and also more resource effective. Okay, then we go more into detail to OpenEO. So why do we need something like OpenEO? And the first problem that we have is a gap in standardization, a lot of different things. So all we want to do is actually solve a real world problem. And for this, we need data. For this, we need a representation of data, some graphs giving us insight over the behavior of a time series, or maps that give us some oversight over larger areas and what's happening there. For this, of course, we need data. For example, the Copernicus data sets, like the Sentinel-1 and 2 mission data, as in this example here. And then these data sets are stored somewhere in some way, for example, in a file system, or in the aforementioned SAR2CUBE, or some other API-based access like Amazon S3 object store. And then each of these can be accessed in a different way and need to be. And when you want to work with these different locations or different data centers, every time you have to rewrite your code for how you deal with the data. You have to write different code for interfacing with the SAR2CUBE file system or cloud storage. And if you have several programming languages, then the number of permutations that you can have between these two are quite large, which means that there are many different combinations that you have to implement when you want to make your code truly interoperable. And the solution to this is actually something that OpenEO is working on, which I will show you soon. Another issue is the data management burden. There are a lot of repetitive tasks that you need to do time and time again when you work with collections of data sets. We see this even in our institute today. A new person arrives, needs to do a research study. The first thing they need to do is search for their data again, download all the same data again, find all the SAR scenes that they want, or all the optical data scenes that they want, download them, then do all the pre-processing again on top of them. And all of this has to be done every time again, and costs a lot of time. So something that we want to avoid and want to make reusable for others, so that if the first person has done it, then the second, third, and so on can reuse that. Another issue is there are quite some cloud services today out there as well, but most of them are not very easy to handle. So quite often you just get access to a virtual compute resource, like a virtual machine, and then you need to start installing your software and everything from scratch again, which is also quite time consuming and takes a lot of time when setting up your processing environment. And you also have to deal with estimations of how many CPUs do you need, how much memory do you need for doing your processing chain. And then in order to run this large scale, you have to come up with some kind of parallelization mechanism that you also have to implement yourself in most cases. And finally, when you work with different data centers, another interesting thing that you will see is that actually the collections that on paper are the same, they are actually not the same. So if you connect to different data centers and send, just do a simple stupid thing like calculating an NDVI or an EVI or something like this on in this example here, a Sentinel-2 analysis-ready data collection, which should be cloud-free and atmospherically corrected. But when we did this, we found actually that in 6 different data centers, we got 6 different results, just because the way of how pre-processing is done is not exactly the same. And then when you have a standardized way of accessing them, you can also start to compare results. So you can look at the results that come out of Google Earth Engine in contrast to the ones that come from the Sentinel Hub, which is on top of the Amazon cloud, or the one here at Eurac in our own database, or another data center. Really, we start make comparisons. So as mentioned before, OpenEO tries to solve this issue with a lot of different permutations between the client's libraries and the different data storage and computing mechanisms through an API. It's actually a RESTful API, which means it works through the HTTP protocol. So you can use that over the internet. And It uses a so-called open API standard for that. So also the way how the API is defined is following an open standard. And another important thing that OpenEO does is it has a large list of predefined processes that you can use, not unlike what you have when you work with the Google Earth engine, where you have a lot of predefined processes that are the same, which actually allows for scalable implementations of these. And then during the project of the original OpenEO project, we started to implement the different components here so that each different programming language can speak this API on the client side, and that there are different backends which offer this API as a service so that you can communicate with them. By the end of the project, we actually found out that it was not so much the work to define this interface, so the API, but that the large work was implementing all of these clients and backend services, actually. And this is what we have set out ever since. As I said, it's now about 5 years that we develop on those. It should also be mentioned that all of this is, again, open source, so all the client implementations and also most of the backends are available as open source if somebody else wants to start using them or adjusting them to their own infrastructure. Another important concept that we have for the description of data sets through metadata, we use something that is called STAC, that's the Spatial Temporal Asset Catalog, which is very helpful for defining the collections, all the properties of collections, so that you can search and filter on the data sets and the features that are inside of them. There's also a paper out there which describes the OpenEO API. It has been published last year by Matthias Schramm, who is from Technical University of Vienna in Austria. He was also the lead of the original OpenEO project, and there we go into more details from the scientific perspective of how the API was defined. So now I try to explain a little bit how processing actually work in OpenEO. So going back again, we want to do our data analysis somehow, and we have our data itself. We have the client libraries to interface with our backends. And very important, again, here, the underlying data model that we use in OpenEO is a data cube. So most of the functions that have been defined up to today are really meant for gridded or raster data. With at least these 3 dimensions, X, Y, and T, which are the 2 spatial dimensions and the temporal dimensions. And for each of these grid cells, there's a feature space, which are the number of bands that you have, the information that you have there. Like, as I said, for example, in the SAR case, the VV and VH polarizations, in the optical case, the different bands of red, green, blue, infrared, shortwave infrared, and so on. What we do with these clients is then you define in an abstract way what you want to achieve with your algorithm by selecting the data and defining an algorithm through a so-called process graph. The graph is basically a representation of all the steps that you need to do for your algorithm to work. You can imagine this a little bit like when writing pseudocode. This is not written in a specific programming language. This is actually just a JSON document which represents in an abstract way all the things that you can do and to manipulate your data set to come to a result. And the nodes in this graph are all these predefined processes that I mentioned beforehand. Later, Michele will give you a more overview of all the available processes there. Then what has happened is that this graph will be sent to one of the OpenEO backends, and these backends take, first of all, care of all the requests that come in there. This is part of the job management if multiple people work there. The next step is for each of the jobs or requests that arrive, the backend will parse the graph and try to understand what you want to do and translate that to something which can be sent to an execution engine or processing engine that is present in a specific backend. Because this graph is not written in any specific programming language, it needs to be translated into something that is then Python, C, Java, R, or whatever, Spark compliant, MapReduce compliant, whatever is the processing engine of your backend. and this translation is then done and executed, and then finally results are made available again through the client so that you can download what you have done, what you wanted done, and check it out. Generally, coming back to the RESTful API, there are a lot of different information that you can get through the API. When you as a user use this, actually most of the time you won't even see this, because the clients in Python and R will do all of this HTTP-based communication for you. All you will do is run some Python or R or JavaScript functions, and they will do all of this request. I just show this to document a little bit the functionality that is there. So the first part is information about the service itself, basically through these endpoints, so that you can see which file formats are there, which version is the backend in, and so on. Then there's information about the data, or via the collections endpoint, so you can see a list of all the collections and details of any specific collection. Then there's a list of all the processors that are available in a specific backend. And then you can manage your process graphs, so your algorithms, by storing them and listing them. Then you can download your results either synchronously, which means you send a request and just wait out for the answer, or asynchronously. This means you submit a batch job, which can run for hours or even days, and then you get notified when it's done, and then you can download one or more results from this. It also takes care of things like authentication for commercial services, also billing. So there's some information about how many credits in some system have been consumed. You can also upload some own files that you might need for your algorithms, any kind of polygons, for example, for limiting your study area, or do any kind of focal zonal statistic operations and so on. There's also a part on so-called secondary web service. Instead of downloading your results in some backends, you're also able to expose them directly as a web service again, so that you can link to your result dataset through a WMS, XYZ, or web coverage service. And then there's also something that is called the user-defined functions. This is actually a mechanism with which you can add own code into processing chains, where you're not limited to only the existing processes, but can set up also your own processes. This is not available in many backends yet, because it's also quite dangerous for a backend to offer the execution of arbitrary code, basically, from a security point. But a few backends are working on this, and we have a few proof of concepts of this as well. But it's not the preferred way of working, as this is also more difficult for any kind of service to optimize code that you haven't seen before. Just again, in the background, the exchange between the client and the server, all of these are JSON documents. So when you get information about the data sets, these are actually JSON documents that describe them in stack format, and the process graph, so the algorithm that you send around, basically, that's also encoded into JSON. So this is the information as advantages, both machine and human readable, so that if there are any issues, you can check these documents also, and they can also be used to store algorithms and modify them later, or share with other people. How does this now actually work? So now we want to do some kind of computation. So there are different clients around. Here's an example from the web editor, where there's something like a formal editor. You can write a mathematical formula, in this case, for example, the calculation of interferometric coherence. And then this will already translate this into a graph-based representation. So that is a convenience tool, so that you don't need to start linking all the blocks here and write every little plus and minus divided and so on in a graph notation, which is quite cumbersome and takes quite some time. So there's this tool that does this for you. Once you have this formula, this needs to be somehow plugged into a larger processing chain, where you access your data set, link different data sets together, for example. And these mathematical formulas, they're usually run in so-called reducers or apply functions, where they can be executed. So this function is actually kind of a nested element inside this node here. And other things that you do in your process graph, apart from accessing data sets and and matching them together is then also preparing them for storing. You can also do statistics, like running a mean over the time series, or you can export them to different formats like GeoTIFF or PNG or NetCDF or JSON, whatever you need as the final output. So there are 3 different main clients for OpenEO. So now you can see that when you actually work with the clients, a lot of the theoretical concept that I've just presented to you, you never see, because when you work with Python, all you see is a little bit of Python code. So for example, you connect to your to a specific backend, for example, the OpenEO platform through openeo.cloud. There you have to authenticate. There will be a kind of pop-up window where you have to put your credentials. And then you select your data set, for example, ground range detected Sentinel-1 data set. And then you put your spatial extent, your temporal extent, and the bands that you're interested in. You might want to apply some filters on top of this, like I only want to have data from an ascending or descending orbit or a specific orbit number. And then you start building your graph basically by just linking and chaining Python functions as you would normally do when you write Python code. So you can just simply write load collection and put all of these parameters that we have defined here in as properties. Then you want to do some of the nicer processing functions that are there, which, for example, to create for you a radiometrically corrected version of the backscatter image based on a specific DEM, for example, the Copernicus DEM. You might want to bring your data into a log space because it's easier to visualize in this way. Just think about the classic distribution of SAR data here, and then it might be easier to visualize it when applying logarithms on them. And finally, you want to export your results, just doing NetCDF. And then the last thing you do is, until here, actually, until this line, nothing has happened in reality, because this, in the background, all this does is writing this Python document, which is this process graph, which I've shown you before. And then with this last step, you send this process graph to the backend to which you have connected in the beginning and start the job. In this case, is example for asynchronous or batch job, and then you can wait until the results are there. And finally, you might see, for example, the area that you had selected. In this case, we have the city of Bolzano, where I'm currently sitting, somewhere here. And then you have your radiometrically corrected terrain flattened backscatter image as here, for example. Other clients exist also in R. For example, it should be noted that this has been implemented also and is available as a pip package. So if you want to install this client, all you need to do is pip install OpenEO, and then it's there. The same goes for R. It has been released as an official CRAN package, so you can directly in RStudio install the libraries for this and then start working with OpenEO. And also in R, the syntax is similar, but here, of course, functions are not linked with a dot operator, but with a dollar, like every R user is used to. So in each client, we try to make it as local to the way people who are used to this programming language would use it. So the syntax and the way how things are working are quite a bit different in the different clients and not look exactly the same. And since it's quite compatible with RStudio, you can get also all the documentation, for example, directly into the IDE. So for all of the functions that exist here, like for example, the merge cubes functions to bring 2 data sets together, then you can directly also see here in the viewer of the function the whole documentation of all the parameters and everything. So it's very well integrated with the IDEs as well then. And the last thing is the JavaScript client, and there specifically there's a web editor, it's called, which is built on top of the JavaScript client. This is for those people who don't like programming. Here you really get a graphical model builder like you would know from QGIS or ArcMap. Maybe you just can build a process graph by dragging and dropping data sets and functions. and link them together yourself and set all the parameters manually through a graphical user interface. And then you can also get directly visualizations of those. Okay, and then just to show a use case example here. So for example, in the original OpenEO project, we one of the demonstration use case that we implemented was based on the mapping of melting snow. And for this, we used maps of snow that we have from MODIS. And then we used time series of Sentinel-1 data to understand at what point in time the snow changes into wet conditions and starts to melt, basically, which can be seen by a change in the backscatter, basically. And then the first part of the algorithm was done by OpenEO to put all of these data sets on a data cube. Then you can do the merging of these data cubes to the merge cube function. Then you can run your algorithm that you need to retrieve the change of backscatter with respect to a reference image in order to understand when they change and go to melting conditions. And then you can do your classification of snow and wet snow, no snow, by applying the snow map as a mask, basically, and then split the snow into snow and wet snow. This can be done by a user-defined function, but also by OpenEO processes nowadays, actually. And finally, once you have done with everything, you can download your results and then use another software like UGS or so to make an animation out of it and visualize it. So in this case, we see now how the snow gets wetter and wetter the more we advance into spring, and in summer, of course, you see how all the snow basically disappears unless it's very high altitudes where it exactly. Okay, the next concept is, this was basically doing processing in one specific backend. Now we are working on doing processing in a federation of several backends so that you can do more. And this is what we're currently working in an ESA project, which is called OpenEO Platform. This is a federation of a few existing services like Terrascope from Vito, EODC, which are also the lead of this project, the Eurodata Cube, which is built from Synergize, EOX, and Brockman Consult. And then also some infrastructure services like ClearDS here in Europe, which all now have created backends for OpenEO. And now the next step is, can we somehow do something so that these can also work collaboratively on problems? And this is our current work on the OpenEO aggregator, so that people are not connecting to one specific backend anymore, but they connect to, let's say, a scheduling instance in front of it, and then based on the kind of processing and data that you need, it will select the best service for you among those that are present in the federation. That's more or less the main idea. There's also then funding available to support research projects to work on this infrastructure, either if you work in ESA projects through the network of resources or through the European Open Science Cloud. So there, people, researchers can go and write mini proposals for getting some cloud resources for do processing on this infrastructure. Of course, hosting and running this infrastructure is not for free, and if you're not Google and have another business from where you get all your money, you cannot offer these services for free to everyone. And then there needs to be some cost that need to be covered by someone in order to pay for the hard disks and the compute nodes and the processing and the maintenance and so on. Yeah. Part of the federation is that everyone can log in through the same way. That is a single sign-on federation based on a concept called EGI check-in, where people can log in and use either their company if they're part of the networks that are in this EGI check-in, or if your company is not, that then you can use also your social accounts from LinkedIn, Facebook, Google, whatever you have, and then use them as your for your authentication. The next thing is the data federation. So all of them I mentioned already before. I use the stack metadata, and the OpenEO aggregator is then able to find all the collections and all the backends that are part of the federation and list them in one common catalog. Sometimes stupid things happen, like in one they're called Korean land cover with capital letters, and the other one in lowercase. They're the same, but they have different names. So there's still some things that the different backends need to clean up their metadata so that this get harmonized. And that's something that we are working on, that later it should be detected that the same collection, so the Sentinel-1 collection, for example, is available in 2 different backends here. And then based on the processes and proximity to you and other factors, it will be selected where your processing will be sent to. In the future, we are also thinking about concepts like cost estimates, so that you simply select the backend which can do this processing most cost effectively. As I said already, all processing is steered through process graphs, and this federation can then also be used during the processing in 2 different scenarios. One scenario is that the same graph is sent to different backends with different study areas. That is kind of parallelization of processing across different infrastructures. And the second scenario is that a process graph that contains data set that are available in different data sets can be sent, broke up into pieces and be processed partially in different data centers to create a better common solution. I will quickly give you some examples of this. So one was here a use case where we wanted to do a crop map for the whole of Europe. In this case, we needed to process something like 5,000 tiles of Sentinel-2 data, which is a lot. Over at least 1 year of data. So we are really speaking about tens of thousands of images that needed to be processed. And then in order to do this efficiently, this process request was split up over running on different infrastructures, so that maybe some country was processed on CreoDS, another country on Terrascope, and another country again on the Sentinel Hub, for example, in this way. And then all of the results were sent back to one location, in this case Vito, who was the company who wanted to do this mapping. The other example is a little bit more complex. In this case, we wanted to do, for example, forest canopy mapping based on what was the name of the model? I'm missing the words here. Maybe it comes back to me. Anyways, we wanted to do a regression model exactly based on very high resolution planet data. For this, we did selected the best locations based on a sampling method here, and then we sent the sample locations to the Euro data cube and the Sentinel Hub, where you can order this commercial data. This commercial data was then generated for us as a private data set in the OpenEO platform, where we could do our analysis of the planet data for finding the forest canopy ratio in the high resolution. This was then done on the Vito backend. And in the end, we have our reference data for our regression model, which is just polygons and the value of canopy, basically. Cover. This is a very small data set in the end, so this is just maybe 1 million pixels or so with a label, which in the end is just like 5 megabytes large for creating the reference data set. And then this was sent to another backend at EODC, where we did then the processing for the full Alps over 120 tiles of Sentinel-2 data. And the final results, so the actual map of the canopy for any point in this region, can then be generated by the user, whoever they're interested. This federation is still growing and under setup. So we have the 3 initial members. Beforehand, Sentinel Hub was already available through Terrascope, but now Sentinel Hub is also implementing their own OpenEO implementation, so that it can communicate directly with this without going through Terrascope, which will be even more efficient and also nice, because this way people can now also develop natively in OpenEO on Sentinel Hub and have higher portability of their algorithms to other infrastructures. We are also working together with Brockman Consult on an Xcube and GeoDB extension that supports more vector data. With this, we bring also more vector cube processing into OpenEO, which, as I mentioned initially, is mainly based on raster data for now. So coming back from the big clouds here again to our small clouds in Eurac. This is the cloud that also Michele will use for the rest of the presentations, basically. So the processing that we do here. So there, what we typically do is we do the pre-processing of our data and bring them into the data cubes. Then we have a few different ways of setting up a data cube. One is through the Open Data Cube software. Another one is through the Rasterman software. This one is a commercial software. This one is an open source free software. In the beginning, we started with this because it was quicker and easier, but by now we switched for most of our development to Open Data Cube because we have more flexibility and can further extend the capacities easier here than in this commercial product. Next to Open Data Cube, we have also built a processing engine, so where we do the actual execution of all of these processes based on Dask, which does parallelization of processes that are built on top of Xarray as the data model. And then we have a common web server which handles all of the requests that come in from the clients and then send them to, depending on where the selected data set in the graph is, either to Rasterman or to Open Data Cube. And we also have some setup for these user-defined functions so that we can run R and Python code in there as well. This, I think I mentioned more or less already. So this Open Data Cube function is really running the processing on top of processes implemented using Xarray as the data model on the back. And then all of the work that has to be done on these arrays can be chunked and processed in parallel using Dask, basically. And here's just some more background about these. So OpenEO processes the graph into Python. Then the Open Data Cube allows us to load data sets and bring them into Xarray. And then Dask allows us to parallelize the processing and run it on a number of compute nodes, as many as we have. OpenEO comes also with quite some extensive documentation, both for people who want to develop their own backends and also for people who just want to use the clients and want to understand how they can actually do work. All of the work is, again, on GitHub, so you can check all the existing implementations here. This is also important maybe for any kind of bug fixing or understanding what's going on with your data. So there's no black box here. You can read the implementation of every single function if you want to. This is maybe also one of the biggest differences to the Google Earth engine, where the actual core functionality is a black box. You don't know how these functions are actually implemented. Here, everything is open source and you can see what's going on there. And you can also copy it and use it for yourself if you need to. It's all on the Apache 2.0 license, so everyone can use that.